Imagine this. A scientist in a lab coat peers at a vibrant, multicolored streak on a white plate. It looks like abstract art, but it's much more. This is a clue, a chemical fingerprint left behind. This, my friends, is the power of adsorption chromatography. Think of a crime scene. Detectives dust for fingerprints to identify the culprit. Similarly, scientists use adsorption chromatography to separate and analyze complex mixtures. Is it a food dye in your candy? A pollutant in your drinking water? This technique can tell us. Adsorption chromatography is a powerful tool used in various fields. It helps us understand what makes up a substance by separating its individual components. This technique is like a sorting machine for molecules. Now, let's understand how this elegant technique actually works. It involves two key components, a stationary phase and a mobile phase. Imagine a crowded dance floor. The stationary phase is like the dance floor itself, while the mobile phase is like the flow of dancers moving across it. In adsorption chromatography, the dancers are the molecules in our mixture. They move with the mobile phase, which could be a liquid or a gas. As they move, they interact differently with the stationary phase, which is a solid material. Some molecules are more attracted to the stationary phase, like dancers clinging to the edge of the dance floor. Others prefer to stay in the flow of the mobile phase, moving quickly across the floor. This difference in attraction is what separates the molecules. Imagine a group of friends with different dance styles. Some love to groove to the music, while others prefer to stand and chat. In adsorption chromatography, molecules with a stronger attraction for the stationary phase will move slower, while those with a weaker attraction will move faster. This difference in speed creates a separation, allowing scientists to isolate and analyze each component of the mixture. It's like watching the dance floor gradually segregate into groups based on their dance preferences. Now let's talk about the different types of adsorption chromatography. One crucial factor that dictates this separation is polarity. Think of it like this. Some molecules are like magnets with a positive and negative end, while others are neutral. In normal phase chromatography, the stationary phase is polar, like a magnet attracting other magnets. Polar molecules in the mixture will stick more to this phase, moving slowly. Non-polar molecules will have less attraction, moving faster and separating out. Reverse phase chromatography, as the name suggests, flips this. Here, the stationary phase is non-polar. Non-polar molecules in the mixture find this more appealing, slowing down their movement and leading to their separation from the polar molecules. Think of it like choosing teams for a game. If you're picking based on height, taller people will naturally group, leaving shorter people in another. Similarly, in adsorption chromatography, molecules with similar properties group, making analysis easier. Section 4. Column chromatography, a versatile champion. Column chromatography is a widely used type of adsorption chromatography. Imagine a tall, slender column filled with the stationary phase. The mixture is added from the top, and the mobile phase flows through it. As the mixture travels down the column, the separation magic happens. Molecules with different affinities for the stationary phase separate into distinct bands, creating a visual spectacle of colors. It's like watching a parade of colorful floats moving at different speeds. Column chromatography is incredibly versatile. By tweaking the stationary phase and mobile phase, scientists can fine-tune the separation process to isolate specific molecules of interest. It's like having a set of filters that can be adjusted to capture exactly what you're looking for. This technique plays a crucial role in various fields. In pharmaceuticals, it's used to purify drugs, ensuring their safety and effectiveness. In environmental science, it helps identify and quantify pollutants in water and soil samples. Section 5. Thin layer chromatography, speed meets simplicity. Imagine a thin layer of stationary phase coated on a plate. A tiny drop of the mixture is placed at the bottom. This is thin layer chromatography, or TLC. It's used for rapid analysis and preliminary screenings. The plate is placed in a chamber with a mobile phase. Components travel at different speeds based on their affinity. This results in distinct spots, each representing a different component. TLC is widely used due to its speed and simplicity. Adsorption chromatography, a silent guardian. Ensuring the purity of life-saving drugs and monitoring our environment, adsorption chromatography is vital. It's a silent guardian, making our world safer and healthier. This technique delves into molecules, understanding matter's composition. Its applications expand, unmasking unknown compounds and ensuring food and water quality. Adsorption chromatography harnesses molecular attraction to solve complex problems.